Hello, welcome to my Introductory Physics Lab 1 Constant Velocity, where the instruction was given to create a movie where we can observe a motion of an object moving at constant velocity, to which a comparison can be made of the same type of motion but being predicted by a computer model which governs the equations of constant velocity motion stated in Newton's second law. For this purpose, I've used a tennis ball with a diameter of 0.067 meters with a weight of 0.056 kilograms. The video was shot in MP4 format, 720p, with a frame rate of 30 frames per second, which gives it a time between successive frames of about 0.33 seconds. I've chosen the plus X to point to the right because it's also the movement of our ball, which you can see here. If I play the movie, the ball moves from the left to the right along the plus X, with the successive locations being shown at the right time step, where we can observe this graph which plots the location as a function of time. All this is done in a time span of initial time 0 to 0.8 seconds. In our program here, we have issued our mass of the ball, which is 0.056 kilograms. We have initialized the ball at vectorial position 0, 0, 0. The velocity of our ball, initial velocity of our ball in vectorial component form, just like this one, is 0.016 along the plus x-axis, 0 on the y, 0 on the left. Delta t, which iterates here in this loop, is set to 0.01 seconds. This exports our CSV file. Now, while the time being issued at 0 seconds is smaller than 0.8 seconds, to this loop where we iterate delta t, the 0.01 time step here, we have issued our net force in vectorial component form, which is 0 on the x, 0 on the y, 0 on the z. This has to be 0 because there are no net forces involved when the object is moving at constant velocity. Using Newton's second law, we predict a new value as the loop progresses. The velocity of our ball is the velocity of our ball plus the net forces acting on our ball divided by its mass m times delta t. We know that there are no net forces involved, so this is 0, which means this whole term is 0, which means that the velocity of our ball keeps its initial value. It doesn't change throughout the loop. The position of our ball needs a new prediction as the time progresses, so we have our initial position of our ball plus the translation being calculated here, the velocity of our ball times delta t, the iteration of our time step. So we run our program, which looks like this. We can see the ball moving towards the plus x direction as our time progresses. The graph is plotted, which shows the location as a function of time. Now this graph combined with this graph looks like this in our Google Sheet production, where you can see the time on the x-axis, location on the y, where we can see the two graphs simultaneously. The red line being the predicted position of our model, the blue dotted line being the observed position of our experiment. Now from this we can draw a conclusion that the observational findings seem to correlate well with the model predictions, although as time progresses, you can see that here, there seems to be an increase in disagreement between the location of our model predictions and the actual observed location. Now this increasing disagreement must be due to a force we are missing or ignoring, which applies a net force to our system that is not included in the model calculations for constant velocity, since we know that net forces are 0 in this case. The discrepancy is most probably caused by friction, which is a contact between the ball and the table modulated by the grooves of the tennis ball and the fiber coating, which means that if we had a perfect sphere, there would be less friction. To a lesser extent, drag is also involved because there's contact with the air, which also makes the ball slow down, just like this one. It gets slowed down. Now, the drag force mentioned here might be negligible since the velocity is probably not big enough, or the cross-sectional area of our ball is small enough to not be greatly modulated by our drag forces. So if we wrap it up, we would say that if we should conduct this experiment in the vacuum of space, far beyond the influences of gravity and friction and drag and sort of, the model predictions and the observation of our experiment would probably be in perfect consistency with each other. That's it for the first lab. Thank you very much.